This is actually one slideshow that's broken into 3 separate parts. So I will post it after our lesson. But if you go to the slideshow to get caught up, or you need to watch it again, or for whatever reason, don't be concerned if there's a bunch of stuff in the slideshow that we haven't covered yet. That'll be day 6 and day 7. Okay. Part of it today, then stop, and then come back. Okay. We good? Solid? Absolutely, the iPad. You don't need it right now. Alrighty, so we did that already. Let's talk about this. We're going to do functions and their graphs. We've done some of this already. You've done all of this already in other classes. I'm just going to give you a quick review on some of the things that you, in air quotes, should already know. That away.
Thank you for your kind consideration.
I'm sorry, what was that?
I was thanking you for your kind consideration.
Oh, you're welcome. So these objectives cover the entire 3 lessons, so we might not get to some of this today. For instance, can you use function notation to represent and evaluate a function? The answer should be yes. Can you find the domain and range of a function? The answer would be yes. And then, can you sketch a graph of a function?
Probably.
Yeah, we've done some of those already, and I've got a couple more later on. When I think day 6 or 7, we'll get to a couple more other functions. And then we're going to do some composite functions later. Nobody likes composite functions, but they're fun. And we're going to solve some inequalities, polynomial inequalities. Those are fun. Talk about piecewise function. What's piecewise function? Beautiful. Well said. And then, of course, we'll review the step function, which you all remember.
Are we going to have to graph the weird, like,
Steppy function thing.
floral ones and
The cardio.
Oh, the cardioids and the
Theta
swirls. I could do those. Those are the ones I could do.
the hearts this year?
Oh, yeah, no.
Okay.
Polar graphing.
Polar graphing, no.
Thank you.
I remember
Thank
that.
you. Like, I appreciate that.
You get pretty pictures, but it's not real relevant for one.
They can actually do what we're not doing.
Yeah, we're on a 2-dimensional Cartesian coordinate plane is the official name.
Thanks.
René Descartes, French philosopher. Yeah. Lot of fancy dancy speaking here. I wouldn't write any of this down because you know it. When we talk about a function, we have 2 parts of that function. We've got a domain, which is all the possible x values, and then that particular point in the domain will generate a range or possible y values for that function. The x is called the independent variable because you can pick x to be whatever you want. Y is called the dependent variable, check this out, because it's dependent on the x that you choose. Pretty clever, right? Yeah, you knew that already. This you know, but you may have struggled with, so I wanted to review it. Let's start with part A. We have a function x squared plus 7. By the way, what does that function look like?
Parabola that's moved up 7.
Parabola, it's your standard mother function parabola that's moved up 7. Okay, none of that is relevant right now. Just thought we'd do a little quick review there. A, what does f of 3a mean?
Plug in 3a for x in the function, and f of x equals x squared plus 7.
Say that again.
Well, f of 3a means they plug 3a in for x in the equation, f of x equals x squared plus 7.
Perfect. So f of 3a would be equal to, John?
3a squared.
Quantity squared.
Quantity squared.
Uh-huh.
Plus 7.
Which would equal
9a squared plus 7.
anything else we can do with that?
I don't think so.
Nope, done. 3 rules you need to be aware of in calculus when simplifying equations or expressions. Number 1, if it's a decimal answer, always 3 decimal places, no exceptions. Number 2, no negative exponents. And number 3, no fractions within fractions. As you start to simplify some of these problems, they can get pretty nasty, and then you enter a cyclic pattern where you can just keep doing the same thing over and over again. Again, if there's no negative exponents and no fractions within fractions, then stop. Part B. What is f of b minus 1? You do that one. And simplify it, don't just plug it in, simplify it. Okay. Good. It wasn't designed to be a very difficult problem. What it was designed mainly to do is I wanted to make sure that you knew how to multiply this out. You'd be amazed at how many people in calculus get b squared plus 1. Okay. If you're one of those people, don't do that again. What is that?
B squared minus 2b plus 1, which is 5b plus 8.
Square the first term, multiply the two terms together, double it. Negative 1 times b is negative b, doubled is negative, whoops.
That didn't happen.
Negative 1 times negative 1 is 1, and then you got a plus 7. So looking around, I think everybody got that as the correct answer, which is good. I did it again. I don't know what you're talking about.
It's a beautiful bead.
Yeah, thanks. Okay, those are the two easy ones. Let's take a look at the last one, part C. Have you seen that before?
I think so.
Yes?
Yeah.
Okay. It's called the difference quotient. We will do a lot of it in this class, which means you need to be able to simplify it for a particular function. So let's just look at this part of the equation or value or the expression. What does that mean? What am I going to do?
Plug those values in for x squared plus 7.
Okay, so I would get what?
X plus, what do you call it?
That's a delta.
X of delta,
No.
delta x.
Delta x,
sorry.
okay.
And then parentheses, squared, plus 7.
Good.
And then you would just do
Minus.
minus x squared.
Hold on. This is really important. Get in the habit of putting a parentheses there. And in fact, you might want to write it down that way. That parentheses is extremely important and also causes a lot of problems when you don't include that. All right, back to you.
So minus, and then x squared plus 7. And then all over, just plug theta x.
Delta x.
Delta x. What did I call it? Theta.
You'll learn. Okay. That's the easy part. Now the hard part, multiplying it out. Again, based on what we learned before, this becomes x squared plus 2x delta x plus delta x squared plus 7 minus x squared minus 7, all of that over delta x. Well, conveniently enough, the 7's cancel, the x squareds and negative x squareds cancel, and we're left with 2x delta x plus x squared. That's an x, that's a delta. Delta x over delta x squared, all over delta x. What do I do next? Factor out a delta x on top. Delta x times the quantity, 2x plus delta x, all over delta x. Whoopsh, whoopsh. 2x plus delta x. All right. Okay, that wasn't too bad. But again, that difference quotient is going to show up a lot. You're going to be plugging that into a whole bunch of different functions. Depending on how big and scary the function is will determine how big and scary the simplifying becomes. Okay. Any problems? Hot diggity. Let's move on. Can I erase this? Did that already. Domain and range. As we said, domain is all possible x values. Since it's an independent variable, you can choose whatever you want for x, except occasionally we'll run into some domain restrictions. In other words, certain values that x cannot be. When we're trying to figure out what x can be in a function, there are two things we're concerned about. What are they? Jane?
The denominator and like the square.
What about the denominator?
Can't be zero.
Good. Okay, so hold on, let me get caught up to you. Boom, good. What's the other thing?
Square root.
What about it?
Can't be negative.
Outstanding, there's both. Other than that, it's open season. As long as the values that you have don't give you a zero denominator and don't give you a negative square root, because we're not dealing with imaginary numbers in here, it's all real numbers. Okay, so for instance, Josh, what doesn't work in that function? What can't x be? And? Well done. 2 and negative 2 do not work in that function. Is there anything else that doesn't work? Nope, that's it. So those are our only domain restrictions. And now you have to figure out how to express that. It would be nice if you could just say x is not equal to 2 or negative 2, but that doesn't cut it. You have to use your friend and mine, Mr. Interval Notation. Anybody want to take a shot at that in interval notation? No? Go ahead.
Parentheses, negative infinity,
Okay.
comma, negative 2, not the bracket, the parentheses, u parentheses, negative 2, comma 2, close parentheses, u parentheses, 2, comma infinity, close parentheses.
Well done. That deserves a golf clap. We use interval notation in there. AP standard is interval notation, so you need to know how to do that. Remember that parentheses do not include, brackets do include. Infinity is always a parentheses. Negative infinity, always in parentheses. The bracket would be only if you're including the value.
Can you read it off one more time? Can you tell me, did it look like this? Can I put my finger in it really quick? Did it
It's
look
right
like
there.
that? Oh, it's right there. Never mind. Sorry. You know what? I'm still learning. Okay.
Somebody have a question over here?
This isn't mine.
How'd you get? So you understand why it's not 2 and negative 2.
Snowflake.
So then interval notation is listing all the things that it can be, not what it can't be. So in other words, I want to be able to explain every single number on the number line except for negative 2 and 2. And so interval notation says go from negative infinity, stop at negative 2, skip over it, pick up from negative 2 to 2, stop, skip over 2, and then go from 2 to infinity. And that's what each of these chunks do. And then the U represents a union or those parts put together. The other thing then is the range, and what are the possible ranges of a function. So I look at that function, the square root of x minus 1, and I know that the domain has to be from 1 to infinity, including 1, because remember you can take the square root of 0, it's okay. 1/2 doesn't work, negative 3 doesn't work, those are all things outside of the domain. And you see from the picture why that makes sense. There's nothing to the left of that function, therefore these things don't work inside the function. So here's our domain from 1 to infinity, and then the corresponding question would be, what's the range? Well, you can see from looking at the graph, if you go from 0, it's going to be all the numbers above 0. So we solid there?
Yep.
Domain and range, not a big deal. 1-to-1 pops up occasionally. 1-to-1 is simply a function that has, for every x value, has exactly 1 and only 1 y value. So something like x squared would not be a 1-to-1 function. Because if y is 4, you have 2 different x's. Make sense? Good. Okay, we're done. I told you it's a quick lesson. Now we need to talk about thank you cards. So let me explain what's going to happen here. I have a stack of